Welcome to the Not Old Better Show. I'm your host, Paul Vogelsang. As part of our Smithsonian Associates Art of Living series, we have the very first in our Pulse of Modern Medicine Insights from NIH Experts programs today. This is a 5-part program that's designed to provide a unique glimpse into the efforts of the NIH. We'll learn from NIH scientific and medical experts about what is currently hot in biomedical research, the science behind it, and most importantly, what it means to our health, the medical treatment we receive today and in the future. We are joined today by Dr. Eric Green. Dr. Eric Green is director of the NIH National Human Genome Research Institute. Dr. Green is known for his ability to demystify medicine, and you'll get a sense today from our conversation of his openness, candor, and ability to take the complex and make it coherent. Dr. Green will discuss the challenges of harnessing genomic data to improve healthcare delivery, ways for the rest of us to gain knowledge and appreciation for this science, and how Dr. Green and his NIH team are driving the way forward in realizing the dream of genomic, data-driven healthcare. Welcome to the show, Dr. Eric Green. Well, as part of our Smithsonian Associates program on health and healthcare, we're pleased today to be with Dr. Eric Green. Eric Green is with the National Institute of Health. Eric, Dr. Green, welcome to the show.
Thanks, pleasure to be here.
Well, Dr. Green, I think for my audience, I think we're all very familiar with NIH as probably the world's research institution. But there are 27 centers focused on research here, and you, of course, lead a team on genomics and the genome research. Tell my audience a little bit about this idea of genomic research, especially when it comes to this phrase that we all kind of know, the code of life. Are you really kind of in the middle of decoding or cracking that code, or are we past that? Is this something that we're still investigating? What's kind of the overall mission of your work here?
Sure. So the National Institutes of Health, as you point out, is sort of the center of the biomedical research universe. I say in a biased fashion, but it really is true. As you point out, we have 27 components, institutes, and centers. We're one of those 27. We're the one responsible for leading genomics research in the United States. The genome is a collection of DNA of an organism or of a cell. So I think of it as a blueprint. You use the word code. I think both metaphors work. And we were created actually by the U.S. Congress to lead the U.S.'s effort in the Human Genome Project, which was this large international effort that took place from 1990 to 2003, which aimed to basically decode, in other words, to understand, to lay out the human blueprint, which of course is scripted in this code within our DNA. So that's why we came into being originally, but of course the Genome Project ended in 2003, and here we find ourselves about 13 and a half years later, and we have ever since taken on a broader mission on behalf of the United States, on behalf of the biomedical research enterprise, and that is to basically understand the genome, to understand our blueprint, to understand how it encodes all this information for creating and operating a human being, and most importantly, to figure out how differences in various people's genomes might play a role in their health and might influence whether or not they get a disease.
That's a really great point. I kind of want to come back to that in just a minute, but what I'd love to do is back up just a second to something you said, and that is that literally it's been a quarter of a century. I'm joining you here in your offices at NIH in Bethesda. I very much appreciate the opportunity to come and see you. Immediately, I was greeted in your lobby by a beautiful mural that depicts kind of this history of the project dating all the way back to Mendel in 1865 and Watson and Crick. I got to see a photo of you and Dr. Collins and, of course, Dr. Watson. But if you could, in your mind, because I'll show a picture of that mural, if you, in your mind, could tell us What is it that's on that mural over that entire period of time that is probably the most significant element? What one or two things would you pick that are just really important?
So that mural reflects both sort of long-term history, very early days of getting the first clues that DNA was the blueprint material for all living systems. And there's a series of accomplishments depicted ranging from the discovery of DNA as a molecule to the understanding that DNA must be the material that carries genetic information from one cell to the next or one generation to the next. And then critically important, and I would say this probably has to be one of the big highlights, was the 1953 discovery of Watson and Crick that DNA consists of this double helical structure. That was pivotal. That was absolutely pivotal. Since that time, there were a series of important incremental advances in understanding how it is that DNA actually operated and actually encoded for biological information. And that then takes us to about 28 years ago, which was the birth of the field of genomics. In fact, keep in mind, the word genomics did not exist in the scientific literature until 1987. It's a very young discipline, much younger than the study of DNA. The field of genomics began just a little over a quarter century ago. And I think the field was named because there was early planning for what eventually gave rise to the Human Genome Project starting in 1990. I would say the next big highlight on that mural and on any timeline for genetics and genomics has to be 2003, when we had successfully laid out the first sequence of a human genome. And I think that will be an incredibly historic milestone we'll look back on decades, perhaps centuries from now, and say that's when it all started. That's when the revolution really started. It wasn't even before then. The starting line for everything we're going to discuss really was when we laid out in 2003 that first sequence of a human genome.
Well, that's a great point that you make, and I read a quote from you that I really liked. You said, "So much of medicine is just based on the average patient." So it seems like really what you're kind of foreshadowing is this idea that we can move towards a better understanding of who we are as individuals, as opposed to just these kind of classes or mass kind of populations. But in fact, there's a term that President Obama used during one of his State of the Unions, talking about personalized medicine. Is that really kind of where that is heading?
Absolutely. And I think what the president actually used was the phrase precision medicine.
Precision medicine.
So there's, and let's just go through these. There's various phrases and they have overlapping meaning. There's genomic medicine, which is basically practicing medicine using genomic information about that specific patient. Not based on the average patient, based on unique genomic information about that patient. Other phrases you'll hear are individualized medicine, personalized medicine. That sort of accounts for variability and uniqueness, both among people and for specific people. But it's not just genomics. It could be aspects of your lifestyle, aspects of your social environment, and so forth. So it takes a slightly broader view than genomic medicine. And the president embraced the phrase precision medicine, which is largely synonymous with individualized medicine and personalized medicine, which just basically reflects, can we be more precise in accounting for unique attributes of an individual patient and tailor their medical care around that? And what are the tools of precision that we're bringing in to the clinic now? Well, genomics is a big one, but increasingly there's going to be better ways of monitoring our own physiology through mobile health devices and other technologies. We're getting better accounting of our lifestyle, how well we sleep, how much we exercise. Some of us wear Fitbits. Those are sort of fun recreational devices. With time, we'll have even better technologies. Can we bring all that together, including environmental monitoring and dietary information, and couple all that and give physicians and other healthcare professionals more precise information about individual patients, so that when somebody walks in the door getting medical care, we don't just put them into a category of an average patient. We're able to get unique information about them, better tailoring their medical care. That's precision medicine.
And so to be precise then with that healthcare, we actually are looking at that individual and maybe even their heredity. Is that all part of this factor?
Absolutely. Well, genomic information and therefore their heredity is part of the precise information we're getting on a patient. And as you implied, and it is important to put on the table, the reason why precision medicine in the long run is where we want to be, even though I'm a genomics guy and I'm putting all of my energies right now into genomic medicine, which I think is a subset of precision medicine, the reason we really want to be in precision medicine is that our health and well-being is not all in our genome. It's not all in our DNA. And sometimes people misinterpret the excitement around genomics as implying that we think everything about health and disease is scripted in our DNA. That's just one part of the equation. The other big part of the equation has to do with our lifestyle, our environment, how well we take care of ourselves, how much we exercise, et cetera, et cetera. And so what we have seen in the last 25 years is a remarkable surge in technologies for studying the genome. So therefore, we've gotten more precise at getting genomic information about patients. What I predict we'll see in the next quarter century are a series of better technologies that will get us more precise information for the non-genomic contributions to health and disease. And I think the president realized that, which is why he got very excited about launching this big initiative called the Precision Medicine Initiative.
So let's talk for a second about costs, because that's certainly on everybody's mind. And we're talking, you and I are talking a few days away from a presidential election where people have been talking a lot about increases for the Affordable Health Care Act, but irrespective of the politics there, it might seem counter, but really this effort is designed to actually lower some of the costs, and some of that might even have to do with lifestyle, because if we understand that through our exercise and through our daily habits and our lives, as well as the lives of those family members that came before us, we might be able to take better care of ourselves, thereby lowering some of those costs. So respond to that. Tell us a little bit about this idea of costs and frame it in some stories for us.
Yeah, well, let me preface it by saying that if we've learned anything by listening to the political debate around healthcare, we quickly realize that healthcare delivery and the economics around healthcare are incredibly complicated. So I don't pretend for a minute to fully understand them. And in fact, I give out research grants to individuals who, in part of what they do, try to look at the economic sort of the implications of these genomic advances. And it is complicated. And in the short term, I don't think we can make any promises we're going to save money. But here's what I will say. When you treat patients in a generic, average way, in an imprecise way, you do a lot of things that I believe we will look back on and say were very expensive, ineffective, perhaps even barbaric. We know that there are many people who get medications where the medications, maybe they don't work, they may make people sicker. And we are learning increasingly that genomic information might better guide our selection of medications for people. We see that with lots of medications for things like, hypertension and mental illness and a whole host of asthma and so forth. But what we also know is, many of the options for treating cancer are incredibly imprecise. We all know of people who may have had seemingly the identical kind of cancer. One got chemotherapy and we just made them sicker and we made their life worse, and it was incredibly expensive, and they ended up not doing very well and weren't cured. And another person you thought would respond the same, and they did incredibly well. One thing we know is it's really expensive to practice imprecise medicine. And so the real hypothesis here is if we get more precise, we get better at this, will we be able to not waste money on dead ends? But that's complicated because, of course, we also have to realize that if we're really successful at this, people will live longer, and then they'll get other diseases, and then there'll be cost to society, et cetera, et cetera. So what I will tell you, and I think you'll hear this from a lot of people who are trained as physicians, as I am, and especially as biomedical researchers, our goal is to prolong life. Our goal is to make people healthier. Our goal is to save patients. And along the way, that may end up saving money. It may end up being more expensive. If people live longer and we have to take care of them longer, then there are societal costs. And we have to figure that out as a society. But, I stay laser focused on how can I improve the care of patients? How can I prolong life? How can we make some of these diseases, obsolete? And what I do know is what we do now is imprecise. And I am convinced that 10 and 20 and 30 years from now, we'll look back on even this current era of medicine, and while it is spectacular, we'll look back on it and say, wow, we figured out ways to do it much better.
Well, there's a lot of talk about brain health today. Certainly, it's very much in vogue. This idea of brain fitness is even out there. It seems to be quite the almost consumerized kind of discussion. And I wonder if you can talk for just a second about some of the work that you're doing with genomics to provide for maybe a more accurate risk assessment on the brain so that we can live a little bit better, higher quality life.
So it's funny, as a genomicist, I study the fundamental blueprint information for living systems. And of course, that's really complicated, and then the brain is sort of the command center for operating a human body, and that's even more complicated probably. But the fact is there's an interplay between them, right? Because the genome and DNA is coding all the information for making a brain and then helping that brain operate. Of course, therefore, there's an intersection. Many aspects of brain health, and that's a very broad umbrella that, of course, would think about, how we do in terms of keeping our mental fitness with age and dealing with age-related mental decline and disorders like Alzheimer's and various forms of dementia is one thing we have to think about. Obviously, mental health becomes a factor within brain health as well. And of course, then there's a whole host of neurological diseases, some occurring early in life and then all the way through the entire lifespan. I think what we're contributing to this is probably analogous to what we're contributing to lots of other diseases, whether it be cancer or whether it be cardiovascular disease, is we are providing approaches and resources and insights to define the genomic component. And it's not going to be absolute, and inevitably it's going to be very complicated for many of these things. But I mean, there are insights being gained. There's a number of neurological disorders that caused by defects in a single gene that have been elucidated because of the tools of genomics. Increasingly, we're mounting bigger and bigger efforts to tackle the much more complicated suite of disorders associated with mental illness, schizophrenia, depression, bipolar disease, and so forth. Really complicated. But some inroads are being made, and some very exciting ones. The problems once thought perhaps not tractable at a genomic level are being found to have some important advances. And then disorders like Alzheimer's, critically important to understand and think about, especially if we are successful at dealing with diseases that affect us at a younger age. Inevitably, we're going to have many more people getting Alzheimer's with time. We've got to figure out how that happens. And there are, again, some important advances. But, I don't think it's going to deliver all the answers. I think it's going to deliver some of the insights that'll be really important. But these things all do interrelate in very important ways.
And I think maybe the word from our conversation today that just jumps out at me is just this idea of complexity, the enormity of all of this that you're talking about, these interrelationships. You start to kind of bring in some of the heredity of individuals, and it seems like technology is playing a larger and larger role in all of this healthcare. It's more a question about how technology is helping you speed up this process to get at some of these solutions, I guess. And that seems to be one of the biggest things out of our conversation is how complex this is.
It is incredibly complex, but where you see the advances come in, it's always because of impressive technologies that have arrived on the scene. We can go back to the 1950s. What was the instrumental thing that helped Watson Crick elucidate the double helical structure of DNA? It was technological advances that gave him those beautiful X-rays. Go back to the 1970s. What was key to being able to start to read letter by letter DNA's code? It was the remarkable discovery of methods for sequencing DNA for the very first time. And then throughout the 90s, we got better and better and better at doing that. And that gave us that first human genome. But what's been the biggest thing in the last 10 years? Easy to answer, because what we have seen are the implementation of revolutionary new ways for sequencing DNA, completely different that was previously available, allowing a human genome to be sequenced for now approaching $1,000. It'd probably be low $1,000 in a matter of months, and being able to be generated in a day or two instead of 6 years, which is what it took us during the Human Genome Project to actually sequence the human genome. That has been game-changing. But what it does is it immediately creates a new bottleneck further down the road. So now we can generate prodigious amounts of sequence data, of genomic data, in other words. Oh, and by the way, we can go off with these new technologies and we'll get prodigious amounts of mobile health data about individual people's physiology. And we'll even collect environmental data with time and lifestyle data. Oh, and by the way, we're now being able to start to crack open electronic health records, which have basically been developing in terms of the infrastructure at sites all around the world, but particularly here in the United States. And that is immense. It's a treasure trove of data. But what does that give you? It gives you massive amounts of genomic data, massive amounts of electronic health record data, massive amounts of lifestyle and physiology data. Now you have a new bottleneck. It's called data. But you know what? It's big data. That's where you see it. And big data was not a phrase that biologists used for a long time. The astronomers had it, the particle physicists, they were big data people, not us, little biologists. But we've arrived on the scene. And what brought us there? Technology. So we're big data people. That singularly is the rate limiting step now for a lot of what we think are some very exciting discoveries. The good news is that technology for better and better data analysis is here and getting better all the time. We've gotten the interest of some of the brightest minds in the world, both in the academic world and in the private sector. And now all of a sudden, all these brilliant computer scientists want to be part-time biologists, and they want to apply the tools of the latest cutting-edge data science analytical methods. And that's what we're going to be doing as biomedical researchers. And basically, in less than a generation, because I think about myself, when I started at the bench as a graduate student, I was at the bench at the graduate student. I was pipetting. I was using machines. I spent 98% of my time at the bench. And I'm still in the middle of my career. Scientists in biology don't spend that much time at the bench anymore. You go to any of the laboratories here at our institute, and you actually see the majority of the people's time spent at a computer. It's still one generation. And that's the technological surge. But now the big technology, heavy lifting, really hard part is data analysis. And a lot is being done to try to improve all of our skills, technologies, and so forth for doing that data analysis.
So, and when you talk about the bench, you're literally talking about a physical place where we can kind of use a pipette, create a slide, look at a slide under a microscope, as opposed to sitting in front of a terminal.
That's right.
And kind of doing that.
Yeah, whether it's a slide in a microscope or whether it's a little device that you squirt some DNA in and you shove it into a machine that sits on your bench and it sequences the DNA. But I mean bench, I mean using machines and devices and pipetting and things that you would typically think of a scientist doing. A biomedical researcher. For a long time, that's what we did. We were in those laboratories. But now, nowadays you go around and you see what biomedical research labs look like. They have just as much, if not more, space dedicated to computer science as they have to what we call, bench science or wet science in terms of liquids and pipettes and so forth.
We're with Dr. Eric Green from the National Institute of Health. Dr. Green, it certainly has been a pleasure talking to you. I think this is just a fascinating subject. I've noticed in my own research of you and your work that you have very much a public-facing kind of component of what it is that you're doing. I found a YouTube channel. I found lots of what I would consider to be very consumer kind of oriented work. What kind of advice would you give to kind of my listeners and really anyone that's interested in learning a little bit more, but kind of starting at a level that's easy enough to grasp and then working their way up to kind of some of the more complex stuff?
So I think your observation's a really insightful one. We are very public-facing, and we're getting more public-facing. Let me tell you why before I answer your question directly. The reason you're starting to see a shift of institute like mine focusing on genomics from just worrying about our science and just worrying about getting these advances and figuring out how to get them applied so that medicine can change. We're moving beyond that. That's important. We're doing that. But all of a sudden, because of our successes, we are finding ourselves not just interacting with scientists. We're finding ourselves suddenly interacting with the medical ecosystem and the healthcare delivery ecosystem. And that is really complicated for lots of reasons, but it brings an important component into this, and that's society. You know, we're not just here in our laboratories just doing stuff that, you know, we'll just publish in the journals. What we are doing, we firmly believe, and we're already seeing it, is going to change the practice of medicine. And we can argue about whether that's going to happen in 5 years or 20 or 50, but it is absolutely already happening. It is changing the practice of medicine. And we believe that the language of genomics and fundamental understanding of genomics is going to become important for any patient, and probably all patients. And if it's important for patients, it's important for all of us, because even if we're not patients ourselves, we have friends and relatives who are patients, which means we get involved in it. And I'm saying whether it's a pregnant woman and prenatal questions in genomics come in, whether it's a patient with cancer, whether it's a patient with a rare disease, increasingly with a common disease, patients who get medications, all these things, genomics becomes relevant. And as a result, we feel a responsibility to help society become literate in the language of genomics, so that when they are talking to their doctor, their nurse, their pharmacist, their physician assistant, and that healthcare professional starts to speak the language of genomics, they're going to be ready for it. And we believe that's part of our responsibility in addition to all these great genomic advances. And so we work very hard to do a number of things to make materials available, to help the general public understand. It's the reason why we worked with the Smithsonian in putting together an exhibition called Genome Unlocking Life's Code. And it's the reason why, associated with that exhibition, which is now traveling North America, we put together a very informative website, unlockinglifescode.org. And that has a lot of material in it for the general public to just become engaged with the basics. We are working now very hard to think about other things we could be doing to improve K through 12 materials to help teachers be able to teach fundamentals of genomics. There's another challenge we have, and that's the challenge of dealing with healthcare professionals. The current generation, like my medical classmates, I graduated in 1987. Remember what I told you earlier? That was the first time the word genomics was used.
Yeah.
I never heard the word genomics once in medical school. My medical classmates have probably 20, 30 more years of practice in them, and yet they're going to be helping to implement this new world of genomic medicine, and they weren't formally trained. We got to deal with the current generation, pharmacists, physicians, all other healthcare professionals. And then we need to think about how do we train the next generation. And so we are very motivated, very engaged in dealing with the general public, dealing with K through 12 science curriculum, and also healthcare professionals. We're trying to develop tools. We have lots of things we're going to continue to do. And hopefully that will help and make this material widely available through whatever means people can access it, whether it's YouTube, whether it's websites, social media, and so forth. And so to answer your question about what can your listeners do, learn. Just become fundamentally literate in genomics. And it's not that deep of a knowledge that you're needed, but just enough to understand the basics so that when healthcare professionals talk to you or family members, and they start talking about, we're going to sequence your genome and we're going to find differences in it, and this is what we're going to do with that information, you'll be able to be informed enough to help make key decisions for your healthcare or your loved one's healthcare. So that's at a minimum, and what we want to see and what we're trying hard to do is just to get genomic literacy improved in this country. And then the other thing, of course, people can do is get excited about this. Be highly supportive of the biomedical research enterprise. Tell, elected officials to be supportive of it. We completely rely on taxpayer dollars to support our work. And finally, to consider participating in biomedical research. The initiative we mentioned earlier that President Obama announced in his State of the Union address a couple of years ago, this thing called the Precision Medicine Initiative, which is going to launch in the next few weeks, probably, literally. is going to enlist at least 1 million volunteers in the United States to be part of a long-term study. And hopefully it'll be more than 1 million, and hopefully it'll be several million. And one of the key things that's going to be needed, both for the Precision Medicine Initiative and then for hundreds and hundreds of other studies where we'll be figuring out how to use genomic information and other types of information to implement precision medicine, are going to be the participation of many, many millions of people in all these various studies. And I think it's incredibly wonderful when people are willing to participate in biomedical research. And it's going to be critically important to have that engagement for the studies that we're going to be doing over the next 1 and 2 and 3 decades.
Well, Dr. Green, thank you. It's an enormous swath of work that you're involved in, and we really appreciate your time and energy and passion, and we certainly are all going to be very supportive. We'll put links up to where we can find some of this great information. We'll follow closely. We're going to highlight several of the other lectures that are part of the Smithsonian kind of program, but this one is our first, and it's a vital one and a crucial one. So thanks very much, Dr. Green, for joining us today. We really appreciate all your time.
Great. Happy to be here. And I should add one more, because I should have mentioned one other website, which is really easy to remember. I gave you one, unlockinglifescode.org. But our own website is set up not only for the scientific community, but for the general public. And it's an even easier one to remember. It's just Genome.gov.
Perfect.
Genome.gov, this is taxpayer dollars going to support, a very important resource to communicate information about genomics to all Americans, and actually all citizens of the world who have access to an internet.
Well, that's great to know too. We'll put links there, but Dr. Green, thank you very much again for your time.
Thank you.
Appreciate it. Thanks to all my guests today, all the help on the podcast. Thanks to all.